All right, all right, all right. Before the drone raffle, we have one last, possibly the deepest presentation. I'm not sure yet, but we have a person here who hasn't missed one IglooConf, I think.
No.
He's been with us every time we've had this. Have we had this 5 times? I don't know. Sometimes.
It feels like more than that.
It feels like more than 5, that's true. Every time this person gives a presentation, after presentation, I think I couldn't do what he just showed. So let's give a huge show of hands to Alan Smith.
Thank you. Thanks for that, Saki. And it's great that I can come back to Finland again and present. It's a bit different in the summer. We can wear shorts. There's no ice and snow everywhere. It's a nice city in the summer. It's good to see that. So what I'm going to be talking about is inside GPT. I've always liked to understand how stuff works. So when I started playing around with GPT, typing in text, and it started generating cool answers, I'm like, well, how the hell does it do that? What goes on behind the scenes? And I've been looking into it and hopefully getting a bit of an understanding which I can share with you. Also, give you, hopefully this knowledge will help you to build better chat solutions using GPT. When my friends were studying computer science, they were building compilers. And the reason that they built compilers is to understand how a compiler works, so they can build better code. And if we can understand how these models work, we can understand why they make certain predictions, why they sometimes get things wrong, hopefully build better solutions. So a bit about myself. I am now an AI MVP. I've been in the MVP program since 2005, hopping around various disciplines. I was Azure before I was AI. I do a lot of work with the community. I've got a YouTube channel. I assist with Coder Dojos, also sometimes run conferences. The session I was going to deliver, unfortunately the demos don't work too well in front of a live audience, but I have got the StarCraft stuff on YouTube. So if you were wanting to see about the StarCraft stuff, you can go in and see how I'm doing that on YouTube. Also, feel free to add me on LinkedIn. I'm happy to answer any questions that you've got in LinkedIn chat if you have any questions about this. Before I start, I really want to thank other YouTube contributors who've really helped to kind of build my foundation knowledge of AI and machine learning and all things related to this. 3 Blue 1 Brown is missing from this. He's recently done some great videos on the internals of GPT, which I highly recommend checking out. So GPT, we go in and we ask it questions and it magically comes out with these answers. So if we want to make cheese, we can ask it how to make cheese and it will come out with great instructions about how this works. So what I'm going to be actually demoing is GPT-2, which I've got running on this laptop. And this kind of gives you an idea of how well the language models have progressed. So I'm going to start this thing without debugging. And hopefully we can have a conversation with GPT-2.
I'm ChatGPT-2, a friendly chatbot. How can I help you?
What's the capital of Finland?
Capital of Finland is a friendly chatbot.
Clear.
I'm ChatGPT-2, a friendly chatbot. How can I help you?
What is the capital of Finland? It's not working too well. I'll give it another chance.
I'm ChatGPT-2, a friendly chatbot. How can I help you?
What is the capital of Finland?
Finnish capital, Helsinki. Finnish state capital, Helsinki. What is the name of Finland? The name of Finland is Finnish for Finnish.
Is it nice in Finland?
Yes, it is nice in Finland.
Why is it so nice?
It is nice in Finland because it is a nice place to live.
Are there polar bears there?
Yes, there are polar bears in Finland.
What do they do?
They hunt polar bears.
How?
They hunt the polar bears.
So around about that time when GPT-2 came out, lots and lots of data scientists got excited because you could actually generate text, and it was kind of revolutionary. But it was only data scientists who got excited. You couldn't really deploy this and have something that people would actually be able to communicate with. But the data scientists realized if we make this thing bigger and we train it with a lot more data, we're actually going to get something that we can communicate with. Now, the only thing that these models do is sequence prediction. So the only thing that the model will do is predict the probabilities of the next tokens or next words coming in the sequence. So if we send the cat sat on there, it will predict the probabilities of about 52,000 tokens, and that's basically what all that the models will do. Now, this is a challenging problem because sequences can be of variable length. And we've also got long-term dependencies in these various sequences. So if we're sending in the cat sat on the floor, it had just been cleaned. It had been cleaned, so it refers to the floor. The cat sat on the floor, it had just been fed, so it is going to refer to the cat in that case. And we'll talk later about the attention mechanism, but the attention mechanism does some really complex maths to kind of figure out the relations between all of the words, so it can make these good predictions. If we have something that's a lot more complex, a really complex sequence, it says the boy stood in the burning deck in the first line of this poem. On the second column, it's saying upon his brow he felt their breath, and the models will understand that his refers to the boy, which was mentioned right at the beginning of the sequence. And this is really what the GPT models are doing. The sequence order is also important. So if we have this set of words, the film was not bad, in fact it was very good, versus the film was not good, in fact it was very bad. Exactly the same words, but we're just changing the order and we're completely reversing the sentiment of that particular sentence. So looking at the actual what the model is doing, I've got a demo that basically shows how the sequence prediction works, and I think it's this GPT fundamentals. So I'm going to set this as the startup file and just run this without debugging. And we'll basically see what GPT-2 is doing to make these actual predictions. So GPT-2 is open source. I've downloaded it from Hugging Face. So if we send the cat sat in the, we get all of the actual percentage predictions for what the next token is going to be in that particular sentence there. So it's saying that floor with 7.64%, and then we've got bed, couch, ground, and so on. And there are about 50,200 tokens in the actual token vocabulary. And we'll look in more detail at what tokens are a bit later on. You can see Helsinki is the capital of, and we've got Finland there with 42.77%. And then Estonia and Russia are down here, so I'm not sure where it's got training data from that. But basically, there is a probability that each of those tokens could be the next one in the sequence. And in the majority of those tokens, the probability is very, very low. It understands languages, even GPT-2. If we're using system dot, then it's specifying, things like runtime, console, security, text, exception, whatever. Any Python programs in the audience? So if you're programming Python, you import NumPy as NP, usually when you're writing Python code. So that's got quite a high probability there. And the king of rock and roll is Elvis. Tokens are not always full words. You can see that Prez is the next predictable token. So it should be Elvis Presley. However, 2.76 chance that they may mean Elvis Costello, because it's got cost there as that token. And sometimes there can be a really high probability. If the king of rock and rolls is Elvis Prez, there's a really high probability that the next token is going to be Lee. My favorite animal is the. You can see that we've got dog here. And if we zoom in way around here somewhere, I think. It's not zooming in on me. Oh yeah, you can see polar there at 0.23%. And then if my favorite animal is the polar, you can see that bear is going to be really, really high probability there. So that's all really that the models are doing. They're actually just working with the probability of these various sequences. Now, a lot of people say that these models are great at understanding text. This is the actual diagram from the white paper, Attention is All You Need, that shows the architecture of the transformer models. And the idea is that we send in text and these things are great at understanding language and understanding text. It's not entirely true. The neural networks don't do text, they don't understand text. So we have the concept of tokenization. We convert our text into tokens. This is something that most people who work with large language models will get. They understand the concept of tokens, that you've got, so many input tokens that you can send in. The model accepts so many tokens, and we pay money for processing these particular tokens. Now, tokens are not words. You can see that the text tokenization, the word token is basically one token, but then ization is something that you can stick on the end of most words, especially if in American you can put ization on pretty much the end of anything and make it a new word, like hospitalization, burglarization, computerization, and various things like that. So what it does is it basically figures out the most efficient way of breaking down the sequences of characters in the training data, so that it can be usable and processable and understandable by these large language models. So, three really important things. Firstly, these tokens are common sequences of characters found in text. They are not words, they're common sequences of characters. And when we say text, we really refer to the text in the training data, which is mostly English. So it's really common sequences of characters that are found in the English language. The models understand the statistical relationships between these tokens. This is really important. I would argue that large language models don't understand language. They understand the statistical relationship between tokens, because the models never see the language. All they see is this sequence of numbers. And as far as the model is concerned, these could be musical notes. We could tokenize music and we could send in, the tokens for different musical notes, and it will predict the next note in a piece of music. As far as the model is concerned, it's just using stats to predict the most probable token. However, this is really important as well, maybe except for GPT-2, but the GPT-3.5 and GPT-4 and later models and the other models that we've got there, they excel at producing the next token in a sequence of tokens. I would argue that that's not entirely true. They don't just predict the next token, they predict the probability distribution of all of the tokens. So these 50,200 tokens, we get the probability distribution of them. And that's important because we're going to use temperature to affect how it actually selects those particular tokens. The last presenter mentioned the word stochastic, which basically means random. Data scientists like to use long words to confuse people, so they won't say random, they'll say it's stochastic, so you have to be a data scientist to understand what they're talking about. But there's a randomization in there, and it will generate random responses depending on what we set the temperature to. So you can see there we've got a sequence of text which we've tokenized into tokens, and if we're in English, it will look like this. It's an array of integers, and that comes out to 45 tokens. You can see that the word "the" is represented differently. So the first "the" does not have a space between it, it has a capital T, and then we've got a "the" with a space between it, that comes out as 363, and then the lowercase, starting with the lowercase t, that's 262. But most of these words, or pretty much all of those words, are individual tokens, prefixed by a space, because it doesn't make sense to have space as a token, because then you probably need about 90 tokens to represent that if space was its own token. Also, the numbers for those, does anybody see any significance about the number representations of comma and dot? It's the ASCII character set, the character codes for those various characters. So the first 256 tokens are just basically character codes for characters. Then that allows it to basically use any type of text. If we go into Swedish, you can see that it's not as efficient at representing the language as tokens. We've now got 83 tokens instead of 45. If we go to Finnish, 103 tokens there. We'll get back to that later on because that affects the efficiency and the understanding of the language. The worst one I found was Telugu, which comes out at 622 tokens. There's only 247 characters. So it's using kind of the character codes where the character is represented kind of by more than one actual token. So this is the actual tokenization efficiency of the language. You can see English is 1.0, Telugu is 8.8, and Finnish is round about here somewhere at 2.2 between Polish and Chinese. And that almost, it kind of correlates, but not really exactly. It's not a straight line if you kind of plot these on a graph. It kind of correlates to the language understanding. For GPT-4, we've got 85% for English and we've got 62% for Telugu. This doesn't show Finnish on there, but Finnish is going to be, somewhere down here somewhere. It's less efficient at understanding Finnish than it is as English. So one thing that a lot of people say is that English is the new programming language, because if you're in the last session, there was mention of prompt engineering. Instead of writing code to tell a computer how to do something, we're writing English in the prompt to actually tell a large language model what type of a response we want. And the code is pretty much boilerplate code. It takes what we want, throws it at the API, gets the response and sends it somewhere else. It's not really doing that much logic. All of the kind of logic that's driving these LLM applications is in the way that we write the prompt. Several reasons why I say that. The GPT models are more accurate with English because the tokenization is more efficient, and also the understanding is better with English because there's a lot more training data in English than other languages. Billing is based on the number of tokens. So if you're sending English to the models, it's going to be cost less than sending Finnish or Swedish or certainly Telugu. Throughput is based on the number of tokens per second, and your quota is based on the number of tokens per minute. And also, models have a maximum number of input tokens. We're developers. If we can make something that's going to be, 20% faster, it's going to cost 20% less, it's going to, be able to process 20% more information, we'll do that. It's an easy win to use English. Now, even in projects where we're working when the language is in Swedish, the input data is in Swedish for our retrieval augmented generation stuff, the output is going to be in Swedish, we use English for the prompts. And we just ask it to provide the output in Swedish. It's fairly easy to do that. And just to give a demo of that, I don't demo this because it gives unpredictable results and it runs very slowly. I asked it how to make cheese in Telugu. This was a GPT chat, and the English, if you remember, the English was quite a good definition. And this is what it came out with in Telugu, suggesting using something called cheese powder, which I've never heard of. Then it gave up. And it switched back to English, and then it offered to create a poem or a story, or if we wanted any kind of other response. Also, here is the image of the Frozen movie characters Elsa, Anna, Kristoff, Olaf, and Sven in an ancient autumn-bound forest of an enchanted land that you requested. I hope you like it. So it kind of thought that when I asked it how to make cheese, that I wanted it to draw the Frozen characters in a mythic woodland setting. Now, that is an extreme example, but it does give you an indication that, there is that graph. As we go down and use languages other than English, it's going to have a better understanding of those languages. So iterating the tokens, we can see the tokens that are used in the model. So if I drop back here and just run iterate tokens, what this is going to do is just basically go through and show you the tokens. Listen, did you hear the bell sound? Because one of the ASCII characters is the bell. So when it prints out that token, it basically makes the bell noise. But as you can see, the first 256 are just basically ASCII characters, and then it gets into bits of words. And as we scroll down, it's basically bits of English words that we've got there. So it makes languages like Finnish by just piecing together these small word combinations. Yeah.
Do you know the size of the vocabulary of GPT-4?
It's about 50,200 and something, I think.
Is it something they disclosed?
Yeah.
Okay, cool. Thank you.
Yeah, so there is a website that you can go to, the tokenizer. So this is for GPT-3.5 and GPT-4. So what we can do is we can just whack some text in there. And that's what I was doing. And it just shows the actual tokens, and we can see the token IDs. And I think it is the same number of tokens that they're using pretty much as they're using in GPT. I'm not sure. Oh, this is coming soon, the GPT 4.0. I'm not sure if they've increased or modified the tokenization of vocabulary there. Okay, so really what we're doing is sequence prediction. Given a series of tokens, the cat sat on there, it's going to come up with a probability distribution of the next token. So it's saying the cat sat on the floor is going to be the most probable token. Now what we can do is just take the most probable token, stick it onto the end of the input, send it through the model again, and we get a comma being the next probable token. We can get the next probable token, stick it on the end, send it through the model again, and is going to be the next token there. So that's what's happening when we are chatting with GPT-4, when we're working in the Bing portal. That's why we see the words coming out one by one. It's continuously running this through the model many, many times to be able to get the next probable tokens. So we can look at the next token prediction. I think that was the demo here, 3A. Let's set this one as a startup file and do a Control F5. Oh, I'm going to change something before I do that, because I understand we've got to make lots of references to polar bears. Is there a prize for the most polar bear references? So what I'm feeding in is my favorite animal is the polar, and it should come out with bear as being the most probable prediction. Enter some text. If I press enter, it's just going to take that, save me typing it in and misspelling it. And you can see like 98.44, we've got bear. Now if I press enter, it's just going to slap the next token on the end, send it through the model again, and you can see that the next probable token is the full stop. And then we've got it's a great companion for me, full stop. I love the fact that I can see the polar bear from the outside. I love the fact that I can see the polar bear from the inside. Yeah. So if the only thing we do is just whack the most probable token in, it's just going to generate, really, really boring, repetitive text. So if you go to a party and you say the most predictable thing all of the time, nobody's going to talk to you because it's going to just be the same type of thing. It's going to be really boring. So stochasticity or randomness, we want to put some randomness in there. And we'll talk about temperature a bit later on about how we can use temperature to vary the output and other things like top P as well. However, it doesn't stop at tokens, because neural networks don't really do integers. They deal with floating point numbers. So what we want to do is to think about word or token vectorization. Has anybody heard of embeddings and vector databases and all of this wonderful stuff? So embeddings and vector databases, this is another way of being able to store information in systems to make them more retrievable by large language models. And the idea is that if I say, what's the weather going to be today, and we're doing a text search, then it's just going to search for those actual words. What is the weather today? And it just basically does a text search or a word search. However, searching by sentiment is like saying, what's the weather today? Will it rain today? Should I take an umbrella today? They all have similar sentiment, but they all use different words. So in some cases, you may want to use vectors for searching, and also for being able to do calculations on words in NLP, or natural language processing. Word vectorization is a thing that people do. Now, cheese, this is the actual embeddings for the token of cheese in GPT-2. It is a big sequence of floating point numbers. I think there's 768 of those. And depending on the system that we work with, we'll have a different number of embedding vectors. We have models that can take text and convert it into embeddings, and then we can compare these embeddings, and we can compare words to see if they are of similar sentiment. We have a project at work where it was loads and loads of news articles, and the customer wanted us to group very similar news articles together. So even though the text was different, we could find that these news articles are talking about the same thing. So we basically did text embedding on the news articles, and then we did some clustering algorithm, and we could actually group together news articles that were basically about the same thing and identify those groups. So a lot of the stuff that goes on when we're doing natural language processing in AI is basically doing maths with vectors that represent these words. Now, we can't think in 768 dimensions. Humans can think in 3 dimensions. We understand the concept of 3 dimensions. We also, because many of us have built websites, we understand about the color space. So Azure is 0127255. That's a color code for Azure. But the way that a data scientist would represent it is 0.51. we deal with floating point numbers between 0 and 1. So this allows us to project colors into this 3D space. And what we can see is that similar colors are basically at similar locations within that 3D space. We get that. But also the same thing happens with words, as we'll see later on in a future demo. Now there's different ways of figuring out if these embedding vectors are similar to each other. You may talk about the Euclidean distance or the cosine similarity, and there's various other methods. It's just basically doing maths to figure out if these words or colors are similar to each other. Now, if we look at the color of Azure, you can see that that's 0, 0.51. If we look at the color dark Azure, you can see that that is sitting along the line as Azure. It sits on that line. And you could argue that this is a similar color to Azure. It's the same kind of shade, but it's just, no, it's the same like color. It's just a darker version of that color. And then cyan, you can see that that's quite different to Azure. And that's in a different space there. However, if we look at the Euclidean distance, which is kind of the distance in 3D space, you can see that cyan is closer to Azure. If we look at the cosine similarity, that's relating to the difference in the angle between those. And you can see that all of the kind of colors that would sit on that line have the same cosine similarity. They're at the same angle. So sometimes we use cosine similarity that compares the angles. So how many people recognize that? I saw a big lot. That's fantastic. I saw a big pile of board games in the Azure office when I was there last night. So Carcassonne. This came from, I was giving this presentation at the DevSum conference in Finland, and before I went on stage, I was talking with another guy at work, and he was talking about vectorization of board games. You know, how can I do embedding and vectorization of board games to find similar board games? And I thought, oh, that's cool. I'll do a slide on that and stick it in my presentation. So I did this just before that. And what he was wanting to do was saying, if you like Carcassonne, what other games are you going to like? So what I'm plotting on here, this is in 2 dimensions. I'm plotting the age and the game time. If we put Star Wars Rebellion on there, you can see that the game time is about twice as long and the age is about twice as old. So that game is not going to be similar to Carcassonne, even though it's sitting on the same angle. Whereas Ticket to Ride is a slightly longer game time, slightly higher age. That's closer to Carcassonne there in that 2D space. So in that case, maybe we'd want to use the Euclidean distance. And there's different mechanisms for doing these actual vector similarities. We can also do something called dimensionality reduction. So if I drop into this website here, which is the embeddings projector, this has a database which is called Word2Vec. And when you start doing file new project with natural language processing, Word2Vec is one of the data sources that you go to. So this is 10,000 words. And what we're going to do is to reduce the actual dimensionality and find what we call nearest neighbors, which is figuring out which words have similar sentiment or similar meaning by reducing the I don't know how many dimensions that they've got. Yeah, they've got 200 dimensions there in each vector. So reducing those 200 dimensions to 3 dimensions. And what this does, my laptop is pretty slow, but what this does is basically puts the words that have similar sentiment together in these similar locations. So if I search for the word October, and I search for 10 words, using cosine similarity, we basically get the months appearing. So these are the nearest neighbors to October. And we can see that they appear round about the same place in this 3D cloud. And then as we go to different locations, I don't know if this has organized itself yet, but electrons, atoms, benzene, and various things, molecules are in the same kind of area in that 3D cloud. And what it will do is basically group together words that kind of mean the same thing into the same actual location there. So that's kind of what's going on in the language model, but it's using tokens rather than words for that actual vectorization. We'll see how that works a bit later on when we go into the actual maths. Now, one of the things that these large language models do is they handle the concept of a transformer, which is a way of being able to figure out what we call the attention, which is kind of how these words are related to each other. So this is what the actual architecture looks like, and it came from a white paper called Attention is All You Need. It's quite a tough read if you want to actually go through it. Another thing that's a bit confusing about the Attention is All You Need white paper is that it was written about translation. It was talking about translating two languages. Well, we can use transformers for translation, but most of the time we're using them for GPT, we're using them for sequence prediction. So you can kind of get rid of this output embedding, which is the positional embedding for the output language, and just focus on this bit, which is the actual input embedding. And this is what happens when the actual it's kind of basically a list or an array of integer values comes in, which is the actual tokens that go into the model. We're going to do the input embedding, and then we're going to do the positional embedding, and then it's going to go into these multi-head attention spans. So we've covered tokenization. We take the cat sat on the, and if we convert it into the tokens, we get these numbers like that. And then what we're going to do is the token embedding, which is figuring out the actual vector, this was it 672 dimensional vector for each of the actual tokens. So we basically do the tokenization like that. Within the model, there is something known as a token embeddings table. And this is just a big two-dimensional matrix of floating point numbers. There's 768 columns in it, and there's 50,256 rows. So for each token, there's the 768 actual embedding vectors. So this is easy. We just basically take 464, 3739, 3332, 319, and 262, do the lookup in the embeddings table, and that's going to give us our actual embedding vectors. And that's basically going to be 768 by 5, because we've actually got 5 input tokens. So that's going to give us the embedding vectors. The other thing that we need to know, because the position of the words is also important, is we need to figure out the positional vectors. So there is another lookup table where we actually do a lookup for the positional vectors. The positional vectors also has 768 columns. However, the number of rows is equal to the maximum number of tokens that we can send in. So if you can send, say, 4,000 tokens into the model, this thing will be 4,000 by 768, and it will pick out 0, 1, 2, 3, 4, 5 for the actual tokens, and just grab those positional vectors. Now, these are created from sines and cosines of various frequencies, and these are basically fixed, whereas the embedding vectors are basically trained, and all those values are set when the actual model is training during the training process. So once we've got the embedding vectors and the position vectors, we can add those two together, and that gives us our encoding input values, which are these actual vectors there. So if we whiz back a few slides, what that is doing is basically this bit here. We've got the input encoding, which is taking the inputs, getting all of the vectors. And then the positional encoding is just taking, you can see that bubble has a sine wave in it. It's using those sine wave-based vectors of different frequencies. And then we've got the add sign, we add those together, and then this goes to the multi-headed attention. Now, we'll cover that in a bit, but what I'm going to do is just step through and breakpoint onto the actual model itself. So, just see how I'm doing for time. Seems to be okay. So what I'm going to do is this next token prediction, I'm actually going to run this in debug mode, but I'm going to change, because I use the example of the cat sat on there, rather than the my favorite animal is the polar bear. I'm just going to comment that out and drop that. And then I can run this in the debug mode. So I've downloaded the source code for the GPT-2 from Hugging Face, and it's written in PyTorch, which is one of the frameworks that we can use for machine learning. I think it's not the original one. I think the original GPT was written in TensorFlow, but this is a PyTorch version of it. And if we go into the watch window, self is basically Python for this in C#, so it's telling us what class we are in. So we're currently in the GPT-2 model, and we're just basically setting up the actual model here. So if I run F5 again, we should get saying enter some text. I press enter, and the text is going to be the cat sat on there. So we're now in the GP2LM head model, and we can see the input IDs. So these are the actual integers for the cat sat on there. If we drop back here, I mentioned that the model never actually sees the text, it only sees the token. So this thing is the tokenizer, this thing is the model, and here we just get the input IDs by calling tokenizer.encode and passing in the text. And then we call the model with the input IDs. So we're just sending that list of integers into the model, and we're getting the outputs from the model. And we'll look at what those outputs are a bit later on. So where were we in the code? Okay, if I just press F5 again, we'll get to the next section here. So here you can see we've got the input IDs. We've also got the position IDs. Because there's 5 tokens, the position IDs are just basically 0, 1, 2, 3, 4. That's just a list of integers there. And this is when we do the input embeddings. We've got this WTE. So self.WTE, this is the actual lookup table that contains the, if I just clear the immediate window, contains all the embeddings. So this is just basically an embeddings table that we've got. And what we're doing is we're just basically passing in the input IDs, and that's going to return the actual input embeddings. So if I step over those 2 lines of code and we go back to the watch window, you can see that the input embeddings is this big tensor, and this is basically containing lots and lots of floating point numbers. The actual dimensions of this is 1 by 5 by 768. Now, when you're working with large language models, they can usually, when you're working with most neural networks, they can usually process a batch of inputs. During the training process, you train in batches. When you're training an image model, you send it, say, 10 images in a batch. So the first number there represents how many items there are in each batch. I'm only sending in 1 piece of text, so that's always going to be 1. The second number represents the number of input tokens, which is 5, and then we've got 768, which represents how many floating point numbers we've got in each vector for the embedding of each token. And then if I step over again, we've got the position embeddings. So the position embeddings, this uses the token encoding, and this is just using the position encoding. We pass in the position IDs, which is 0, 1, 2, 3, 4, and then we get the position embeddings. And then the next thing to do is to add these 2 together. So the input plus the position, that gives the hidden states. So that's a kind of representation of the words with the actual kind of meaning or the sentiment of the word, which is in the embeddings, and the position of the word. So we know what the words mean, and we know which position they are in. That's giving us 2 of the things that we need. But what we also need to know is kind of how the words relate to each other. And that's really what goes on in these multi-headed attention blocks. Now, you can see that there is an NX, and basically in GPT-2, in each multi-headed attention block, there is basically 12 attention heads, and there are 12 layers of attention heads. So there's going to be 144 of these multi-head attentions. So the same kind of attention calculation is taking place 144 times. So what goes on in there is this actual maths. This is the actual formula for doing the calculation on attention. And it works by using a query, a key, and a value. And what it's really doing is taking each token in the sequence, comparing it to every other token based on some type of a criteria of how those actually relate to each other. So to generate the key, query, and the value, we take the encoder input values. So this is the stuff that contains the meaning of the word, or the sentiment of all of the tokens and the position of all of the tokens, and that's 1 by 5 by 768. We send it into a convolution layer, and this is going to be different for every one of those attention heads, and there's 144 of those. So dependent on the actual numbers that are set in the training for the convolution layer, we're going to get different representations of the input that are going to be used in the attention mechanism. So this is coming out as 1 by 5 by 2304. It then goes into a split operation to get out the keys, the queries, and the values. So this is going back to 1 by 5 by 768. The top one is the key, the middle one is the query, and the bottom one is the actual value. Now, because there's 12 heads, we then actually split that vector into the keys, queries, and the values for each of the 12 heads. So that's 1 because there's 1 batch, 12 because there's 12 heads, 5 there's 5 tokens, and 64 of those because that's what happened when you divide 768 by 12. That gives you the key, the query, and the actual value. And those are actually used for calculating the attention, which is how the words relate to other words. So, Saki, can you stand up, please?
Yes.
Yeah, so if you imagine that we're processing everybody in this room, and we're all tokens that are going on, and what we've got to figure out is the relationships that we have to one another. This will happen for each person in the room, but right now it's happening for Saki. He's going to be the query. So he's a current token that the model is focusing on. And then the key is going to be a token from the input sequence that the model is comparing to the query. So each person in the room is going to have a comparison to Saki, and it's saying, okay, how do you relate to Saki in some way? And the value is really how we're actually doing that comparison. So how many people work at the same company as Saki? So there'll be quite a strong relationship between the people who work at the same company as Saki. How many people have been drinking with Saki on an evening? Lots of people there. How many people have survived? The others are somewhere else. So for every kind of, in every attention head, it's kind of doing a slightly different comparison of how it relates to that. And you know, you may have gone to school with Saki, you may be his neighbor, you may be in the same darts club as him if he plays darts. And all of those different relationships, all those different attention heads will look at a different way of being able to actually compare those words. And it will basically build up a kind of a strength of how much connection you have to Saki based on all of those different bits of information. Thanks for that. You can sit down again. So that's really what's going on in the attention span. Now, it's kind of easier to explain the concept of what it does rather than the maths of what goes on behind it, because it's all vector maths. Basically, everything that goes on with working with neural networks is processing these really big vectors. This is really good because everything that goes on in the graphics for 3D games is about processing the same types of vectors, which means that gaming cards are really, really good at being able to do large language models. And because there's millions and millions of gamers in the world, a lot more gamers than there are data scientists, it means that GPUs aren't as expensive as they would be if gamers didn't use them for 3D maths. I also heard that, was this yesterday or the day before, that NVIDIA is worth more than Germany currently. The NVIDIA stock price is more than the German stock market. So NVIDIA is doing well out of this, and a lot of this is driven by, you know, having to do all of this maths to be able to train these models. But basically what we're doing is we are multiplying the query by the key. We're then dividing that by the root of 64 because that just seems to work better. And 64 is basically the actual number that we've got here. And that gives us, once we've put it through the actual softmax algorithm. And softmax is just a way of ensuring that all of these floating point numbers in all of the rows and the columns will add up to 1.0. And what that's giving us is the words and how the words relate to each other using different criteria. We then multiply it by the value and we get this, which is the attention. Now that basically has the meaning, the position, and what's really important, the relationship to other words in the sequence. So we can see a bit about how that maths works. I think my breakpoint is still set in the code. So if I go to the next breakpoint, you can see here, this line of code is basically getting the query, the key, and the value. And it's doing a couple of operations at once. I think I said on the slides that it does, if we drop back to the slides and I whiz up a bit. It goes through that conv 1D, and then it does a split, and then it does the actual split heads. And it's doing all of these operations at once to give out these keys and queries and the values. So if we drop back to the code, this is basically using the convolution there, passing in the hidden states, and then it's doing the actual split. And then we do the query, the key, and the value doing the actual split heads here. So that basically splits it up into the 12 heads. So if I step over that row, we should see that we've got the size of the query, the key, and the value, 1 by 5 by 768. And then when we do the head splitting, it's splitting in my head all of this maths. We've got the 1 by 12 by 64. So that's basically going to be those attention heads. Now, if I keep pressing F5, you can see that this is happening a lot, because there are 12 layers and there's 12 attention heads in each layer. So it's going to have to be 144 times until we actually get the output. And then that's going to be what the actual output is with the actual predictions of those word probabilities. So go back to the slides. So we've done that calculation and we're getting out the actual values from that. And what's kind of happening in the maths, if we could go in and see and visualize and understand this, we've got those two sentences I had as examples earlier. The cat sat on the floor, it had just been cleaned. The cat sat on the floor, it had just been fed. So if you mention the word it a bit later on, what does it refer to, or what does he refer to, or she refer to when I'm talking about something? Maybe it was something that was mentioned earlier on. So these actual tokens will have their vectors, their sentiment vectors. And if we assume that this is in 2D space rather than 768 dimensional space, they will basically look somewhere like that sitting in this actual space. And they'll have a certain distance from each other, and the closer that the words are together, the more connected they are. We saw that when I was looking at that visualization cloud. All of the months are in the same shape. All of the kind of scientific words are in the same place. So the word it hasn't actually got any kind of attention to any other words. It hasn't kind of been linked to any other words. But these attention calculations, because we're taking the first example of the cat sat on the floor, it had just been cleaned. When we've been through all of these layers, it will modify the vector values of it to put it to closer to floor and closer to clean. So it now is more similar to floor than it is for cat. Now, it could be mentioned several times, but it's the particular instance of that token within that actual sequence that is going to have its sentiment shifted, dependent on where the other words and how it's connected to each other words. So that's really what's going on within the attention mechanism. And as I mentioned, there is 12 layers, and there's 12 attention heads in each layer. It's also doing a bit of the normalization and feed forward and softmax and so on towards the end to actually figure out what's going on in the actual network. Now, we can actually visualize this. There is a great website. I think it was part of the Hugging Space stuff. But it's this one here, and what this is doing is actually displaying a visualization on the BERT model, which is fairly similar in terms of complexity to the GPT model. So what we see here is the various sentences, and you can see all of the connections between the words, and you can see the actual view of the model. So these are all of these attention heads. You can see that it's 12 along by 12 down. And it's kind of showing graphically the actual connections and links of all of these words. I've not really experimented with it that much to see all of these actual values, but what it's doing is kind of providing the internal visualization of what's going on with the attention in all the different layers of that network. So that's a site that you can go on if you do want to experiment with and explore how that stuff works. So, how can we parameterize this and get better results? Because we don't want it just repeating and just giving the most probable token. So we've got something called temperature. And the sampling temperature can be between 0 and 2. And higher values like 0.8 will make the output more random. Sometimes if you go up to 2.0, the output just gets completely corrupted. So I wouldn't recommend going much above 1. The portal usually prevents you from going above 1. But using temperature, that can also affect the output of the model. So I've got a temperature demo here. If I go to temperature theory, set this one as a startup file and just do Control F5. Remember, this is GPT-2. It's not that great at doing predictions, but what this should do is basically show, with using a temperature of 0, you can see that the text is coming out there and it's very repetitive. As we increase the temperature, the randomness or the stochasticity, I love that word, of the actual outputs is changing. And here, by modifying it and pumping up the temperature, you can see that we're getting more creative outputs. You can also get inappropriate outputs. I've been doing this presentation, suddenly the whole audience falls about laughing and I have no idea why, and something inappropriate has come up on the screen. So I'm a bit concerned about this. But you can see that as we push up the temperature, we do get more creative outputs there. But we've also got other parameters that we can modify. So if I drop back to the slides, We've also got, basically there's maths using softmax. If you played around with neural networks, you will know what softmax is. As I mentioned, it's a way of being able to get a series of floating point numbers into a percentage distribution. And by dividing by the temperature, that modifies or shifts the magnitude of that array. And that will affect the probability distribution because it's using logarithms and stuff like that. It's a nonlinear function. And this, I saw that and thinks, well, what if temperature is 0? Bad things are going to happen because it's a divide by 0 exception. So in that particular instance of the model, you can't use a temperature of 0. You just use a very, very small number, and that will affect the probability distribution balance. So I've shown that demo. We've also got top P, which is another mechanism for being able to actually control the way that we get the probability distribution. So top P, if I specify a top P as 0.1, it will only select from the top 10% of the actual answers. So if the top P is 0.1, it can be floor or it can be bed, and it's most likely to be floor, but it can never be couch. With a temperature of 0.1, it could be couch. I've got an animation that shows how that works. And top P is basically used as an alternative to temperature, or it can be combined with temperature to limit the actual results and stop it from generating unpredictable tokens. You can see here that the top P is set by default to 0.95, which means that the 5% of really obscure tokens that it shouldn't be giving outputs to are not going to be returned in the output. So just to finish off with, I created just during lunch break, I think, this actual animation, which basically shows what happens as we modify the temperature and modify the top P. So you can see when the temperature is 0.75, and as we increase the temperature, the probability of floor is increasing here, and also the probability of floor is increasing slightly with the top P. But when we start to get around here, you can see that the actual probability of these tokens are actually disappearing from the probability graph. The way to think of this is when you go to the fun fair, there's one of those wheels that you can spin, and there's a tiny little wedge which is the top prize, and that's the probability that it's going to land onto the top prize unless they've put a weight on the wheel. But kind of like spinning one of those things, that's going to show what's going to come up. And as we reduce the temperature in the top P, it affects these probability distributions in different ways. And you can see as we go down and as this approaches 0, then the actual probability of it being floor is going to get to 100% in both cases. But it has kind of different ways of modifying the probability distribution there. So hopefully that's been a good introduction to the GPT and the large language models. I will be around if anybody's got any questions. Thanks very much for listening. And I understand that Zaki wants me to show some kind of thing that we've got to do something with.
Let's not do it yet. First, Alan Smith.
Thank you.
And then you can do this. And after you guys have, well, you can start doing it, of course. But to stream, we thank you for attending and following IglooConf, and we wish you all the best. Have a nice weekend. Adieu.
Thank you.